So now let's look at some data for this. Here we have someone throwing a ball up from the edge of a cliff. The ball leaves his hand at 30 meters per second upward, positive 30 meters per second. It rises. Every second it gets 10 meters per second slower, reaches the highest point after 3 seconds. At that point, its velocity is 0 meters per second. Now it moves downward, and now it gets 10 meters per second faster every second. By the time it reaches the same height at which it left the hand, its velocity is the same in magnitude, 30 meters per second, as when it left the hand, but the direction of velocity is different. When it left the hand, the velocity was upward, now it's downward. The direction of velocity is always the same as the direction of motion. So in the beginning, it was moving upward, so its velocity was upward, positive. Now, it's moving downward, the velocity is downward, negative. Carries on falling, still gaining 10 meters per second downward every second. For this entire motion, the acceleration is g, 10 meters per second squared downward. So while it's going upward, we could say in common language it's decelerating. In scientific language, we'd say it's accelerating downward, meaning that the fastest speeds of that interval is experienced when it's most down. So we can say the acceleration's downward, even though it's moving upward. Now, when it's moving downward, the acceleration's also downward. Again, the fastest speeds are down. Remember that these negatives don't mean less than 0. So minus 40 here is a faster velocity than minus 30, because it just means 40 down, 30 down. Doesn't mean less than 0. Notice that at each height, the velocity is the same in magnitude, just opposite in direction. So as I've pointed out, at the starting height, 30 meters per second up, 30 meters per second down on the way down. After 1 second, at that height, 20 meters per second up, and then on the way down, when it passes through that same height, 20 meters per second, but now downward, and so on. Now remember, of course, that acceleration due to gravity isn't really 10 meters per second squared down. It is 9,8 meters per second squared down. So let's look at this data again, but in the more actual values. And although the numbers are not so nice now, the patterns are still there. Every second, the velocity gets 9,8 meters per second slower as it's going upwards and faster as it's going downward. In other words, the acceleration is always 9,8 meters per second squared downward. And again, we can see at the same height on the ball's upward and downward motion, the velocity magnitude is the same, just the directions are different. There's another pattern we can see in this data, and that's called time symmetry. Let's take, for example, the ball's motion from leaving the hand to its maximum height. And it takes 3,06 seconds. For the ball to fall back down that same distance also takes 3,06 seconds. So it takes just as much time to move a certain distance up as to move a certain distance down during free fall. And that's not surprising because it's got the same acceleration whether it's moving upward or downward. And so it takes just as long to move a certain distance whether it's going upward or downward. Because remember, moving upward or downward is part of the same kind of motion. It's projectile motion whether it's upward or downward. So in this movie, we've focused on the fact that projectile motion is motion in free fall. In other words, when the body is only moving under the influence of its weight. And that doesn't have to be downward. That can be upward. It can be stationary for the instant it's still at the top of its motion. Or it can be downward. And for all that time, it moves in the same kind of way, as in it moves under the influence of gravity at acceleration due to gravity, g.